Okay, good morning, everyone, or evening, or night. Today we have an exciting topic, verification in SysML V2. So what we're going to do is we're going to do a quick overview of what verifications are, and we're going to see how we can use CATIA Magic and Magic Model Analyst to evaluate verification cases to see if they satisfy particular requirements. And we're even going to take a look at a really fun example. So this example here is from the SysML V2 evaluation overview car braking analysis. This is one of the samples that you have access to if you go into help and show samples in the tool and you go to SysML evaluation overview. So we're taking it from there. It's car braking analysis. Verification is now built into the language. So it's another type of case that we are using to be able to pass in a subject, a particular objective, which is the requirements that we're actually verifying, stopping distance and brake heating here. And then we are going to be able to return a verdict. And we use this pass if, which is also built into the language. The SysML V2 language spec itself has this pass if, and we are going to evaluate and return a verdict kind, which will give us a pass, fail, inconclusive, or error. Okay, so with that, let's talk about our particular example for the day. So, I'm a huge fan of pickleball. I hope all of you are too. But in uh, in today's pro pickleball, we have a few different issues that have come into light with the materials that are used in the paddles. And so the USAP is a standard board for pro sanctioned events in pickleball, and they have a few different rules that you have to follow. One of them is called the paddle ball core of restitution requirement. And so I've talked to a few different people who design their own paddles now, and I don't see too much. It's more about the feel. They kind of go to the factory, tell them some overall specs, and then they deliver a paddle, they play with it, and they iterate on that. We want to see if we can use a little bit of engineering to actually be able to calculate some of these values to see if we can create our own paddle based off of different, and we can actually interchange the different materials and core and come up with a passing PBCOR. Now, just so that you're aware, I'm not a material science major, so I actually did use AI, Gemini, to come up with some of the equations for this. So it's going to be a little bit hand wavy and maybe not exactly 100% accurate, but it will give us an overview of how to use verification cases with a fun example. So we're going to create assume and assert constraints for a requirement. Our requirement is going to be a passing PB core. We're going to create a parts decomposition for a particular paddle. So we're going to omit the edge guard, and we're just going to have like the face sheet, the core, um, as parts of the paddle itself. And then we'll create a verification case and link that verification case to a requirement. And then we are going to create a satisfy requirement for that so that we can evaluate and show pass fail. Again, PBCOR, this stands for paddle ball coefficient of restitution. And what that means is how fast does the ball come off of the paddle? In the manual, we need it to be less than 0.43. Using Gemini, we came up with this equation. We have this reference, this C reference, and this is just a constant that is a derived number that kind of calibrates our calculation to match a real world test data that's available. So this is a little bit hand wavy here. It's used to kind of balance out the unmodeled variables that we can't take into consideration for this. And then we're going to use the Young's modulus for the face sheet and the core. And so this is a calculation for the stiffness of a particular composite material on the front and back. We're only going to focus on the front face sheet, assuming that it will be the same for the back. The higher the value means the stiffer the face, and these are in gigapascals. We're not going to do units for this, but we could. And these are numbers that are known. They've already been tested, so we can actually use we actually have a little bit of accuracy here. So we're going to sum those together and multiply it by the thickness of the core, and then take that to the third power and do a cube root there. So once we do this, we will have our estimate for the PBCOR. So let's see what this looks like. A couple things to note here is we'll be using these initial values for anything that we want to change. So when we're doing evaluation, if you want to be able to play with certain numbers, you need to use this colon equal sign in order to get your initial value. Okay, so let's go take a look at the model. Okay, so we can see here, this warning up here is just showing that I put this in the textual notation, so when we expose the elements, these elements automatically pop up. You can use the SysML V2 textual notation in order to do this on a view. So if we go down and we look at the view, you can see that I'm exposing those elements, and then I am rendering it as an interconnection diagram. It's not anything too complicated, and it won't get you it looking exactly like what I have, but it will be pretty close, and then you can show particular attributes or variables. You can expose those separately. Okay, so we have modeled the paddle, we have the core, the face sheet, and we have the satisfy requirement for PBCOR test, and this will point to our requirement, the paddle shall not exceed 0.43 PBCOR. So we're using the paddle as our subject, and we have this require constraint, paddle P, which is the paddle, and then .PBCOR, which is referring to this attribute here, should not be less than or equal to 0.43. Okay, and additionally, we have the verification case here, and we have a verify of that USAP PBCOR testing, which is this requirement here. Okay, so we have everything connected together. We have the different attributes that we talked about in the presentation that are all for the core, the face sheet, and the paddle. And then we have our actual calculation here shown, PBCOR. And we see that these are all reals. And then you see real default because we have this initial value. So when we calculate this, we can just click anywhere and we can hit evaluate. And we'll see we get a passing for the PBCOR. We have a value of 0.3797. So now if we changed this constant to something else, let's just say it became 1, then we could see real time, we could see it grow. So let's change this back to 0.0041. Okay, we have our value. So now the thickness of our core is 15 millimeters. So if we wanted to decrease that thickness, then we could show that we have a lower PBCOR, or if we wanted to raise it, then that would also impact in the opposite way. So let's change it to something, I don't know. We don't have too many that are 17, but let's say 17. We could still get passing with these particular values, but say that we changed our face sheet from, I don't know if this, maybe this was carbon fiber. I can't remember if we wanted it to be like fiberglass or something. Say it was some lower value. I'm not sure. Then we could see that this value goes lower based on our calculation. Okay, so that's how the evaluation works. Additionally, we could, in another video, I will show how to actually build this. And then, so we'll see how to build all of this from scratch, and then additionally, I can show how to use the REST API to manipulate these values. And if you have a working Jupyter notebook, we can get these values as well.